Oh, yes, we will be starting shortly. I'll just try to. All right, looks like the stream is alive. So I guess we'll get started. Oh wait, I was told. Sorry, give me a. Yeah. Anyway, yes, everyone. Welcome to the live event of the competition. I'm Eating Jane. I'm the guy you probably have interacted with the most on the forum or over email. So I'm a PhD student at Carnegie Mellon University. And then I just want to, so a lot of you want to know like how the competition is organized and a lot more details in the background. So I figure I will start by giving a presentation on that. So the introduction, I guess this doesn't really need too much introduction because you guys have all been participating, but for the sake of people who are watching the stream, so the goal of the competition is to find a good generalization measure. A generalization measure, roughly speaking, predicts how well a model will generalize. And then, so you can imagine a function that takes in the model and also the final data. And the training data. And then you want to predict what the error of between the training error and what the difference between the training error and the test error is. And then, however, since deep models are extremely over-parameterized, the community has had a lot of trouble trying to find good generalization measures for deep neural networks. And then we also observed that when people derive these theories in practice, oftentimes they only test it on a very small set of model and then reach the conclusion that are not necessarily robust or transferred to new tasks. So our hope of organizing this competition is to push the field forward by using a large and very unified benchmark, so we can measure progress concretely, and also making a compute that would otherwise be unavailable to a lot of people available. So with that being said, I want to talk about how like a bit more about how we design the tasks that we use in this competition. So you might know that the competition is separated into many different tasks. Yeah. So every task, the way we design it is it has a very particular connectivity pattern. Let's say the screen one is what networking network would look like, and then these the red and the yellow one is roughly speaking what we call the pyramid net in phase 2. Sorry, not in phase 2, in phase 1, which you have not. You don't have access to them yet. We are experiencing some licensing issues, but we will make them available soon, I promise. And then so and then finally the blue one here is the VGG model. That also you should be very familiar with. And so to run a competition like this, it's very important that all these models have the same or very similar training error. The reason is because there's actually a lot of training error. There's actually a huge amount of signal in the training error if you do not train your model to what we call the interpolation regime, where your model predicts every training data accurately. of course, in practice, that is very hard to do. So what we did is we said once the model goes over something like 99% training accuracy, we will stop the training. So all the model is on an even ground. And if you want to predict the test error, you can do it by simply looking at the training accuracy. So now I want to talk about the different phases of data. So in phase one, which is the two data set that you when you submit your solutions on the Coda Lab over the three months or so, this is the data that your solution was being tested on. So the models are, roughly speaking, they're fully convolutional neural network with no downsampling. And then so this is a quite unconventional model, which is good for testing robustness of measures. And then we have a global average pooling at the end of the model, and then batch normalization at every convolution layer. And the data set is scenic10. Scenic10 is, roughly speaking, it's supposed to be a replacement for CFAR10, but it's collected at a time after CFAR10. So people have been observing that the distribution of natural images shift over the internet, and then scenic10 is a pretty good test if you want a replacement for CFAR10. So all the models are trained for 3,000 epochs, and learning rate is dropped by 0. It's multiplied by a factor of 0.2 at 1800, 2200, and 2400 epochs, and the learning rate start with 0.001. And then we also have a lot of hyperparameters that you can check on the GitHub page if you want to. But the main difference between the two tests is actually just so actually one of them has batch normalization and the other one does not. So this is an interesting case because batch normalization, as you know, that has a significant effect on the performance of models, and then we thought, but also at the same time, if you include them in the same models, observe that it's kind of hard because batch normalization fundamentally changes the statistics of the model. So in this case, we separated into two cases, and then so a lot of methods did very well in the phase one data, as you can see on the public video board. Now we want to talk about the phase two data in details. In phase two, we have 4 tasks, and then you only had 3 chances to submit, which I will admit is a very challenging task. But I think our belief is that if you want to something that's really robust, this kind of almost zero shot matter is appropriate. And then we were very pleased to find that a lot of people were able to find solutions that even work in this case. So the first task in phase two, we used the flower data set from the Oxford, and then we downsampled it. It has 102 classes, which is much higher than anything you've seen in the private or phase one. And then we used a similar networking architecture with a slightly modified hyperparameters. And then the training is also pretty standard. But one interesting thing we did is that during training, we with 50%, we randomly apply auto augment onto the training data. In this case, so which usually improves the model performance, and then we were trying to see whether the measures can accurately capture that. Even though now the training and the phase one or the public data set contains data augmentation. And similar case is for phase two, where we use a very similar networking architecture with a difference that we added a dense layer on top of the global average pooling at the end. And then we use the Oxford PEST dataset, which has 37 classes, which is also that is also much higher than the previous one. We also applied a similar data augmentation policy where we apply auto augment to have the data. And then this is trained using some standard training schedule with these hyperparameters. If you are interested, they are on the GitHub website. In test tree, in this case, we use a more standard data set, FMNIS, fashion MNIS, which you should probably be familiar with, and then just VGG-like models. And then, so there's no data augmentation or anything happening here. It's very standard training. But the interesting about this data set is that all the models actually perform quite well. So the difference in performance is small, and then which makes the problem also quite challenging. So finally, in task 4, this is also it's a very standard procedure, network with CFAR10. So in public data, you also had a CFAR10, but it was on VGG. So in phase 2, we decided to just also train network on CFAR10, and then we applied data augmentation on all of the data, just random flips and random crop, not auto augment. And then standard training procedure with SGD momentum. Yeah, so these are what the 4 phase 2 tasks consist of. And then onto metric. You guys are probably also pretty familiar with the metric. So the high level idea is measure correlation, but in a way that is robust, and also it will filter out quote unquote non-causal features correlation. So if you're interested in detail, which I'm sure most of you have already read, is you can read the paper that Ben-Am and I wrote for ICAR 2020. And in this year's NeurIPS, there was also another very interesting paper by Carolina and Giguitz and Alex Julian et al. It's improved the procedure on this, what we did here, which is also quite interesting. They also did quite large experiments. If you're interested, you can take a look. So now I want to talk about the competition itself. The competition is so organizing the competition is actually quite a interesting challenge in itself. I must say we were not expecting this larger number of participants. Certainly not how many submissions were made to the competition. So we had to, I guess, improvise along the way. So what we observe is that so there are more than 100 participants who made at least one submission. And then we received a total of 1,700 submissions, which overall consumed about 200 GPU days of compute. And then, so the runtime of the solutions are varied by model. So we saw one cluster of solutions where they just finish within 1 to 2 hours, which is extremely fast, and some solutions that take a very, very long time, like 5 to 10 hours. And there's actually not that many solutions that lie in between, which I thought was a very interesting observation. And then the infrastructure itself was largely built on Colab, which is very flexible. They exposed the full backend of the computer to us, including the data submission pipeline. Also evaluating protocols and how the machines communicate with each other. It's fully open source and then very high degree of freedom, which was very helpful. And then the computer workers are hosted on the Google Cloud's Kubernetes engine, which auto scales when there are a lot of compute. Auto scaling is very crucial for having a large number of submissions, as you can see here. So most of the time, it's very spiky. I observe a lot of people, I assume because they have quite similar working hours, they submit at the same time. So at peak, we had things like 12 workers running at the same time, and then at low, we have probably just 1 workers alive. So this kind of auto-scaling infrastructure is very crucial for running computation at this scale. Yeah, so if you would like to learn more about this, I would happy to be I will be happy to chat. And then I also want to just make some high-level comments on how, or like, what are the observations we observe in the competition that may not be clear to you guys because you don't see all the submissions. So one of the most, I guess, perhaps not that surprising thing is that data that were prepared, solutions that were prepared on phase 1, they did not do, or their performance are overall worse in the phase 2. As you have seen before, these the data sets that are presented that are almost complete out of distribution. So the fact that it still performs so well is it's actually really surprising to me, and then I'm pleased that I saw some solutions they actually generalize quite well from phase 1 to phase 2, even though the performance is overall lower. Like I said, in the fashion case, the task is actually quite hard. And then we also observed, I would say, 4 overall themes that people took to approach this problem. So the first one is representation analysis. So approximately, like and this is also the method that kind of won the overall competition, is that you look at the hidden representations of model, and then you perform some kind of analysis. This research direction is generally underexplored, but I think it's very promising. And then I'm glad that this presentation, this competition showed that. And then the second approach is, which a lot of people took, is, and it's largely responsible for the high performance model solution in the phase 1 data, is doing data augmentation. So a lot of, which is a perfectly valid solution. But the interesting thing is when you have a huge data shift, like, so let's say in CFR10 you have these data, and then you have a certain augmentation strategy that worked well, but then now suddenly your data is a fashion amnest or flowers. Even though they're technically all images, the strategy to augment them are actually quite different. So it is an interesting problem, like how one would design an augmentation strategy that will approximate test error for images in general. And then finally, we have some solutions based on capacity measures from the first principle. And this is a very difficult task. That said, the community has been spending a lot of time on it. In general, we did not see they performed that well in this competition. But not to say we should not be looking for one. I think we should. It's just that, like I said, it's a very difficult problem, and then it's gonna be at least another 5 years ongoing effort. And the last one, so I forgot to write it here, is have a parametric model. What that means is that you take your model and you will extract some kind of meta features from a model, and then you train predictor, like let's say a linear regression model, all these meta features, which is we also saw some very interesting approaches, but ultimately it did not seem to perform that well. But maybe there are improvements that can be made. So that is all I want to say about the competition. If you guys have any questions, feel free to ask right now. I and a few other organizers are here right now. You can also type in chat if you want to, if you don't want to speak.
So one question that I had was, concerning the architectures, did you guys had an idea of why using the networking network was interesting, or why did you favorize this type of architectures compared to others?
Well, it's like network here is just something like it's a very general like we say network, but it's actually quite different from the original data. It's just a connectivity patterns that we have is also more parameter efficient than the other. We did try BGG, but BGG generally has much more parameters. And then like there's kind of the phase one data was actually not related to network architecture at all. It's not a this is not a model that you would use in practice. Like these are number of channels. These are actually not the resolutions. It's fully convolutional with zero downsampling. So we I guess it's kind of So I guess there's no particular reason why network is interesting. It's just one. If so one shortcoming we had was we cannot use skip connections. Because because the way the combination was set up, and then if we use skip connections, a lot of it's very hard to write a complex measure that can handle arbitrary computation graphs as far as we're concerned. So to get enough interesting things, we just picked like some of the more representative fully like this kind of no skip connection models. So VGG is one of them. Network, we have a lot of them, but in the end we picked these because we found them to be the most interesting ones. I guess that's, I don't know if that answers your question.
For sure. Thanks. I agree that like ideally we would like to use like skip connections and ResNets and things like that, but it starts getting very complicated to tell like people to use these graphs that are not like completely sequential and to not give away what is the network that is being used and things like that. So,
well, in the sense that I think that is okay, but the harder problem is like it becomes really hard to write one. I think to handle arbitrary graphs. That's So for the first iteration, we just decided we will be using this. I guess a more simple version. Yeah, and then networking element just happens to be a pretty cute architecture.
Yeah, for sure. Thanks.
Yeah, no worries. Any other questions? Or you can type in chat if you don't want to speak. Yeah.
I have one question. So is there any theory that investigates whether you can actually predict validation set performance from training data and the architecture alone? Like in this competition, we've been looking at whether we can predict test error from the available data, which is the network and the training data. But is there like any research or like just theory in general that's looked at whether this is a feasible task to begin with, that whether you can actually accomplish this task given only the information provided, and perhaps like are there bounds on the exactness or the approximations you can make on the test set error?
Well, yes. So, I mean, the VC's theory suggests that if the bound is tight, if you have infinite data, right? So it's definitely a problem that is doable. At least if you have a very small hypothesis class. The problem with deep neural network is that it's unclear. Well, first of all, you have your model, your hypothesis space is much larger than the number of training examples you have. And then, so in that regime, it's technically unclear if it is possible. But then, if it's impossible, then there's no point of studying generalization deep learning, which seems a pretty grim outlook. And then my personal belief is that yes, I think you should be able to find something that does well, and then I guess certainly in this competition we have seen that some of them do better than the others. I don't know if that makes sense, but yeah. So there's no theory there's no theory that works well,
Right.
which is why we are holding this competition to see like what people come up with. The deep learning theory community at large has been deriving these bounds from the first principle, which is Pack-Bayesian bounds or these things. But none of them work well in practice, which is what we have seen.
Right.
And then so we're thinking like if you're willing to forego this measurement from the first principle, and then maybe we can find something that works well in practice first, and then try to derive a theory about it. Yeah, that's I guess the guiding principle of this competition. Like a lot of extremely smart people, much smarter than I am, have been trying to derive like good generalization bound, and then the conclusion at the end is none of them work that well. So maybe it's good that we look for some other approaches.
Okay, thank you.
I thought I would add something. Maybe this is like a good topic for the roundtable then, but I think part of that question could also be, right, like what else could you use, right? It doesn't have to be just the training data. So certainly like data augmentations, right? That's using some other external information to actually get the generalization bound. So if you frame in the framing of the problem, it's not just the training data and the network. It's actually our assumptions or our ideas about what the function should be doing, right? So like augmentation, for example, makes the assumption that the network should work with rotated or perturbed images. That's a prior. And so if you frame the problem that you also include priors, it's a very different task than just saying, data set and architecture.
Yes, indeed. But then now you can ask questions. What if we include language, or what if we include tabular data? Then in that case, it's very like data augmentation is actually an unsolved problem in those regimes, right? Like in this task we pick image recognition because, well, it's the most popular task. But in reality, you actually want something that will work that's fairly generalizable. Or you can restrict the universe of your models to say, okay, I only care about image recognitions, I only care about natural images. Then yes, you can use data augmentation as much as possible. But then the question is, well, you can always just train your model with data augmentation. Why then? What is the point?
Yeah, no, I agree. Yeah.
Right. Yeah. Anyway, yeah, we will have a roundtable at the end. So here, I guess I want to answer more questions that I guess only I have answer to.
So if I can ask another one.
Yeah, go ahead. Yes.
Concerning the release of the data sets and everything, do you know if it's going to be possible to have all the data available? Because for the moment, only the descriptions are available.
Yes. Ultimately, yes.
Yeah, it'll be available. It's just a small technical glitch, but it should be ready next week.
Okay, no problem. It's just that I would love to go in that, like deeper in the analysis to why our model worked and what could have we done to do better in the final task and everything like that. Because at the end, as we did not know how long it took to run our models. We ran a very simple one at the end, and when we got the results, we saw that we could have been using more data and possibly getting a more robust results. And this is something I would love to analyze.
Yes. They will be available soon. Yeah. So everything in phase 1 and phase 2 will be released. So it will be at the same place as the where the model descriptions are. You can just download it from like a Google Cloud bucket.
Okay,
I think that's a good question as well. In the public data set, our sort of measure that did the best was quadratic in the number of classes, and we didn't expect that the number of classes.
Oh yeah.
So as a result, we also had to run a very, very simple model, but we didn't know beforehand, right? So
that we that is an oversight. We did not expect that.
Could you tell us if the best solutions were maybe linear methods or quadratic methods?
I have not read too much in details, but their write-up will be released. Or I mean, they did give a presentation. I don't know if you were in the actual NeurIPS like 2 hours earlier.
Yeah, no, I saw it. I think some of them made sense. I think some of them are linear, but some of them also seemed quadratic too. But I thought maybe you had like a meta-analysis, or maybe you'd.
Yeah, sorry, I haven't had a chance to look into them. I mean, I was doing a lot of final exams and everything. So, but by the next week, I hope to go through all of them, and then I will also post all the write-ups onto the main website. Please just keep an eye on it, and we'll be announcing everything on Twitter. So, yeah.
Cool, no worries. Thank you.
Yeah. Yeah. Questions? More? Actually, when are we scheduled to have the first talk? Oh, so the second presentation, unfortunately, said he cannot attend. So I guess, what time is it right now? Actually, we should probably start. So it's S. Mesnar here?
Yes, I'm here.
Okay. Yeah, feel free to present anytime. Yeah. Can you present?
Yeah, I can.
Okay, cool. Yeah, I just want to make sure you have the authorization.
Hello, thank you for having me. I'm Sebastian Mesnar, and I'll present the solution me and Blaž Krl submitted to the competition. In our approach, we assumed that there doesn't exist a complexity measure that only exploits one part of the model and gives a good generalization score. We believe this because deep learning models are very complex, and often humans lack intuition behind them. Instead, we created a few simple metrics and combined them into the final score. Each of these metrics returned a score between 0 and 1, and we tried doing some measures that they exploit the different parts of the model. These metrics are arbitrary, so they can be added or removed if needed. Okay, so the metrics we considered are the following. We use the non-uniform weights, or the percentage of weights that have changed for more than the standard deviation, the normalized difference between initial and trained weights, the distance between a simple classifier and the deep learning model, the margin, where we returned as a score the percentage of training examples where the models where the probability of the best performing class and the second best performing class is bigger than 0.2. We also use the mean of variance when the classifier is trained for a few epochs with different learning rates, the distance to the variance mean when the classifier is trained for a few epochs with different learning rates, and the categorical cross entropy. Because these combinations of metrics might not be trivial, we automatically tested them. each metric in a test was given one of the three values, 1 if it was given as is, -1 if it was given as 1 minus the score, and 0 if it was not acknowledged. So the score for that metric was 0. When testing these 3 to the 7 different combinations, we saw that the best combination was where the learning rate was given the combination value 1. The non-uniform weights were given also the combination value 1, and the learning rate mean was given the combination score -1. When looking at the results of these evaluations, we saw that the best performing ones were very similar. So, for example, the best was the one that is given on the slide, and the second best was maybe this plus one other, like margin had 1 or something similar. And this further gave us confidence that this was the best performing combination. This was all from me. So thanks for listening. And if you have any questions, you can write them to the emails shown on the slide. Thank you.
Hi, Sebastian. So I had one question. So how did you combine these measures after like assigning them the score of 0, 1 or -1?
So we simply summed them and divided them by the number of metrics that were acknowledged. So.
Oh, okay. I thought you like made a parametric model on top. Okay, but you summed them. Okay, got it. Thanks a lot.
Thank you.
Cool. Is there any other question for Sebastian?
Yeah, I was wondering what score did you reach on the phase 2 datasets with this?
We were 8. So I believe it was something around 5.8 or something like this. The 8th place overall.
Any other questions? We do have some. Well, actually, we're a little behind on schedule, but yeah. So Idle Banner shows that he cannot present. So it's FCL and blank here.
Hi. Yeah, I'm here.
Yeah. Okay. Yeah. Feel free to present. Yes.
Okay. Just one moment. Can you guys see my screen?
Yes.
Is it a full screen? Because sometimes
yeah, it's full screen. Yeah.
Okay,
yeah,
that's
yeah.
great.
Yeah, looks great. Thank you.
So hi, I'm Lin Feng here. So yeah, I'll be presenting on behalf of the team FCL. Basically, it's the first initial of our names, Zhang Lin and Sao Huan. So yeah, what I've been using is, first of all, I would like to thank the organizer for hosting this very nice competition. Yeah. So I have presented the method we have been based on. It's about asymptotic stability. So yeah. So okay, so I just spent a bit of time going through the background theory. The details you can see in this paper, but just going through very briefly. And the background theory is like if you treat the neural network as a dynamic operator rather than a one-shot operator, you can retrieve the asymptotic stability by looking at whether it's chaotic or stable asymptotically. So the previous work we have demonstrated like both theoretically and empirically that actually this kind of amount of asymptotic chaos directly leads to overfitting. So the way you do is like you just iteratively apply the neural network on a certain image iteratively. Then you can have a time series, right? For each epoch, you have a trained model. Then for each model, you have a like time series. So the two different colors represent the time series of the original image and the slight perturbed image. Yeah, so you can see if it's ordered, they always like lock in phase. They oscillate together. And you do see kind of like a periodic oscillations. This is what we call just order phase. And when they're just different, I mean, in epoch 7, so in this particular model, they just become different. The two different colors, they separate from each other. So this is chaotic. And yeah, this is asymptotic phases because you see, I ignore all the first more than 100 evolutions. So a prior work shows that actually for a broad range of image CV models, so you do see that actually the models during the training, they go through a stable phase to the chaotic phase where asymptotically, yeah, and the edge of chaos is where the test loss is the most minimal. And as the stability decreases, the model gets more and more unstable. You can see the generalization gap increases. So this is adapted from the previous work. And this measure, of course, you can compute the theoretical measure as well, which is the normalized asymptotic Jacobian. When it's 1, it's actually the model is somehow the most optimal. It's also the edge of chaos, asymptotic chaos, after you mentioned that. So because according to algorithmic theory, actually this kind of treatment is quite independent of the input data you have, because no matter where you start the iteration from, it goes into the same algorithmic attractor. So it usually doesn't really matter. So even it's on ResNet and DenseNet with like batch norms and stuff, you get the same phenomenon. But the issue is the previous work was carried out on a very specific constraint where the input and output of the operator or the extracted component from the model needs to have the same dimension for this kind of asymptotic stability to be computed or accessed. So that's the challenge for this, actually, for most of the real neural network people use, because the input and output dimension are not the same. So we tried two methods to approximate this, to tackle this problem. One is simply this original network. We add an upscaling layer to restore the dimension from the output to that of the input. And so we tried a couple of different methods, but the one seems to work really well. Not really well, it's just better than the others. It's simply just a matrix multiplication layer without, it means a full connected layer to the output layer without bias or any sort of non-linear activation. But you just have to be careful that in order to, for this upscaling layer to mimic the operation of the whole network as close as possible. So you need to put the weight matrix as the Jacobian matrix of the whole neural network. Of course, the dimension is different, so you need to transpose it. But of course, in order to avoid divergence or convergence quickly, you need to normalize the whole Jacobian, the weight matrix by this factor. So this is, and then is the input dimension, and now this output dimension. And this just simply the F norm square of the Jacobian, input output Jacobian. So yeah, so basically the revised dynamic operator is simply the original dynamic the network, like multiply, just doing a matrix multiplication. So what we did is the complexity score, we defined it as the distance of after 10 iterations, which is not really asymptotic stability, but it's not too far from it. So yeah, the divergence of the two trajectories where x and x prime are just like any input data and the slightly perturbed version of it. So just a like simple illustration of the effectiveness, but of course the final effectiveness is represented by a score, which I'll show later, but just illustration. So for for one model in the computation in the public data set, if you have the model without regularization, you add some regularization, and you add more regularization, you can see both the generalization gap decreases and asymptotic distances, which represent somehow the asymptotic stability of the network decreases as well. But of course, method one was not good because we artificially add a layer that somehow, and it's a linear layer, it's not nonlinear layer, so it somehow doesn't reflect totally what the original network is. So we thought about how to even do it without doing the upscaling, but still trying to get some intuition from the stability perspective. So one way is look at it is, well, from the network, you have an input-output Jacobian. You can look at the kurtosis of Jacobian. Why? Because it seems that if the Jacobian has a fatter tail distribution, which means there's a higher kurtosis, the fatter tail tends to stabilize the overall dynamics. It's not really strictly, but it has this tendency to stabilize the overall dynamics. So that leads to better generalization. This is actually a very simple to compute measure. It just compute input-output Jacobian, you compute the kurtosis. So it looks like there is a trend here as well. So as you can see, without regularization, and you add more regularizations, the kurtosis of the input-output Jacobian increases. So the tail is getting fatter, and the dynamics is supposedly getting more stable. And you do see that generalization gap decreases as well. So this are overall scores. So using some asymptotic distances, we tried, there are two submissions we did in the final phase. They scored like about these scores in the public data set. And the final score is around 3 point something. And the kurtosis outperformed this method by a fair bit. So this is our final ranked score in the final phase. But there's some interesting phenomenon we find after the computation that it seems that it put a negative sign in front of a kurtosis, the public data set scores improves quite a bit. But we didn't have a chance because the computation was over. We didn't have the chance to test it on the final data set. But I guess later there will be a chance to test it, right? So yeah, and with that, I just thanks everyone for attention. Just open for any more questions.
Yeah, hi. So I had one question. So a bijective transformation should not change the score, right? Because mutual information should not change.
I mean this one, right?
Yeah.
Yeah, we thought so too. So we don't quite understand why that's the case.
Okay. Yeah, flipping a sign it shouldn't change the score at all. I mean, I am pretty sure about that because I have tested it myself. Yes, that's interesting. I mean, the code is exactly the same. Yeah, that's kind of interesting.
But we haven't exhaustively tested it. It might be like a random distribution.
But yeah, this could be because of the random seed, right? Because you are not testing on all the samples, right? You must be taking a subset of the training set and checking on that, right?
Yes, we only did on a subset. Maybe that's why. Yeah.
Yeah, because if you, I was gonna say if you just feed in like some random numbers, you will see that flipping a sign should not change the score at all. Yeah.
Right. So that being said, this method it does depend on the input data set, but this method doesn't matter too much because the ergodicity of the asymptotic phase. So maybe that's why. So this is more random. Yeah.
Okay. Cool. Is there any other question? Because if there's no more question, we'll have a 10-minute break. So we'll come back at, well, I guess 3 p.m. EST, 12 PST, and whatever. So in 10 minutes.
Okay, thank you.
Well, I guess I just show this slide so there's something to look at. All right, see you guys in 10 minutes. Hi, is Vashisht here?
Yes, yes, yeah.
Okay, cool. Thank you. Yeah, you can. I guess you can wait a couple minutes before people come back, but otherwise, feel free to start whenever you want. Yeah, it's 1:03 now. I guess you can start.
Okay, hi. So hi everyone, I am Dipen Morwani. So me along with my lab mate Rahul Vashisht and our guide Professor Harish Guru Prasad, we participated in the PGDL competition. We tried various methods and the one based on noise resilience helped us in securing 5th position in the competition. So I'll describe the various methods that we tried and finally report their performance on different datasets. So the different kinds of measures that we tried can be broadly classified into 3 categories. These are noise-based, margin-based, and norm-based. So first of all, the noise-based measures are basically defined using the property of noise resilience of the intermediate layers of a network. So layer is said to be noise resilient when adding noise to its inputs does not change its output by much. So the main question is, why do we expect a trained network to be noise resilient? So the intuition is that the intrinsic dimension of the data manifold is expected to be very, very less as compared to the ambient dimension. So if the neural net has trained well, that is its neurons get activated only by receiving the data from this manifold, then when we add a uniform spherical noise, most of it should get attenuated when it passes through a layer. So many of the recent papers as well have used this property to establish generalization bounds, as well as this has been shown to hold for multi-layer linear nets under certain assumptions. So now, as this was defined for a specific input and for a specific layer, so we took their arithmetic mean and geometric mean to define 2 measures called mean noise stability and geometric mean noise stability. Similarly, we can also define the noise resilience of the output layer with respect to the input layer. Using these, we define 2 similar measures called mean noise stability output and geometric mean noise stability output. So now we move to margin-based measures. So first of all, we know that margin can also be defined at all the intermediate layers of a network. So first of all, we tried to use input layer margin as a measure, where so this is basically defined as the minimum perturbation which we need to add to an input X, so that it is finally misclassified by the network. Similarly, a recent paper introduced the notion of all layer margin. In this, we are allowed to simultaneously perturb all the layers of a network, and this is defined as the minimum norm of these perturbations, so that the perturbed network misclassifies the input. So clearly, this definition inherently takes into account the compositional nature of a neural net. So as we could not find any closed form expression for this, so we approximated it by performing gradient ascent on the loss function with respect to these perturbations. So we also defined a measure called margin Jacobian by combining output layer margin with the Jacobian of output with respect to these intermediate layers. So the exact definition of this measure measure can be found in the PDF that we will share. Now we move to norm-based measures. So in recent times, multiple generalization bounds have been established for neural nets based on different weight norms, such as spectral norm or L2 norm. So the main thing that helped us in evaluating these bounds within the time limit of the competition was to use power method for estimating the spectral norm of a convolution operator. So this method doesn't require us to explicitly create the sparse weight matrix representing the operation. Instead, we can work with an abstract linear operator for which we just need to define the matrix vector product and the matrix transpose vector product. So using this, we defined a measure called fast log spec, which was inspired from a recent work. So now we'll report our results on different data sets. So the matrix that was used in the competition was basically the mutual information between the predicted measure and the generalization gap. So one thing that can be clearly seen is that different measures perform well on different tasks. So on task 2, all layer margin works well, while on task 4, margin Jacobian works well. Similarly, on private data set as well, although geometric mean noise stability outperforms the other measures, but its performance on task 8 is very bad. So overall, we think that we still need to further analyze these results to understand why some measures perform well only on certain kind of tasks. So that's all from my side, and these are the references that we used. Thanks.
Cool. Any questions?
Could you provide some more discussion of the Taylor expansion that
yeah, okay.
Why do you need a Taylor expansion, or what's the reasoning behind it?
Okay, so basically it's not easy to we are not using the output layer margin in this case, which can be easily seen as the difference in the scores at the final layer. We want to find the margin in the input space. So for that, we to exactly calculate it, we basically need to find the distance from the input at which basically the classification of the neural net chain changes. So it's not easy because the function is very complicated. So basically we just use its first order Taylor expansion to find the closed form for this around the given point x. Around the given input point x, we just Taylor expand the neural net to its first order to get this input layer margin.
Oh, thank you.
Yeah, in interest of time, I think we should move on to the next presenter. If you guys have questions, you can always just on Slack reach out to each other.
So I'll stop sharing them. Yeah.
Yeah. Is Samuel here? Is there a Samuel in there? Oh, I don't think Samuel is here. Or I guess I can let the next person present. Is Inverse, Team Inverse here?
Yeah, we're here. Let me turn on my video.
Yeah, cool.
Sorry, I'm trying to share my screen. It just takes a second sometimes.
Yeah, no worries. Yeah.
Cool. Can you guys see this?
Yes.
Okay, great. Thanks for the opportunity
Can
to
you try
present.
to zoom in so it's not full screen yet?
Okay, let me try that. I think my, let me try one more time. Yeah, I have two monitors, so you know how it goes with Zoom. Okay, I will just share my thing, and there's a transcript below, so you can just read it. Does it look good now? Okay.
Yes. Yep.
Yeah.
So yeah, thanks for the opportunity to present. The title of our approach is Local Measures of Distortion. And so, you know, I'm hopefully not going to just read this transcript directly, but basically it looks like many of us had the same ideas of generalization, especially thinking about the internal representations. And so maybe speaking to what was talked about in the spotlight or keynote by Dr. Aurora, we're really interested in these measures of generalization that are central and rooted in theory, even if like tangential measures of performance or generalization work well, for example, on image classification tasks, using this sort of finite size data set, which, you know, it's only a small portion of the full space of models that are possible. So I wanted to start by talking about generalization from the perspective of approximation theory. And so in approximation theory, we measure generalization as the maximum error between the target function f and the approximation f, let's say f star, over the whole domain. And so what that implies is that in order to measure the true generalization performance, you really need samples over the whole domain. And obviously it's infeasible to do in high dimensions due to the cursive dimensionality. Even if you had a generator, for example, that could generate all possible input images. And sort of I wanted to pause here because I think this is an important question. We talked about it maybe in the start of this sort of session, but are we sure this is even possible? And I wanted to give an example from you know, a classical example where it doesn't work, right? So in polynomial interpolation, for example, if you're given n equispaced points on -1 to 1, for some functions, for example, if you wanted to approximate the sine function using a polynomial, you can do it to arbitrary accuracy, given enough points and degree of the polynomial. But for some functions, such as the Runge function, which is shown over here, which is actually very smooth and has an infinite number of derivatives, we can prove that you get arbitrarily bad generalization performance, particularly at the edges of the domain, even as you increase the number of sample points. So, you know, for this particular case, for the Runge function, it actually can be fixed in many different ways, maybe by using different training data points. These sort of equispaced points are particularly bad for some reason, using different basis functions or imposing additional regularity, such as like a smoothness constraint or using least squares. But the point is that this exists even for very, very simple functions, right? So looking just at the training error really isn't enough. You really need to look at something more than that. And so, you know, jumping ahead a little bit, looking at these measures of regularity or what do those imply about deep networks, and what can we learn about their generalization performance? Well, so for example, the work of Moscar and Poggio, starting maybe in 2016 and maybe even a little bit before that, what they basically showed is that if you're given a target function f and you're trying to construct an approximation f star, but you know the true compositional form in the form of a directed acyclic graph. So it's like a sort of feed-forward network with no current connections. If you use that graph structure of the real function, the true function f, in the approximation, so you make your neural network architecture mimic the same structure as the true function, they prove that you can avoid the curse of dimensionality with respect to the order of the approximation, so the number of terms you need. And what they showed is that you can get provably good performance near the training data by penalizing the maximum derivative of the nodal functions or even the whole network. And so without tooting my own horn, in my PhD, what I was able to show is that, or what I was able to develop is sort of a differentiable technique based on minimizing the Sobolev norm of the network rather than the maximum derivative, which wouldn't be differentiable. And by minimizing the Sobolev norm, then you can actually use this together with SGD. And there's a theorem that goes along with it, which basically says if you use the graph structure, you can get provably good performance, which depends on both the smoothness of the target function, but also on the smoothness of the approximation. So sort of what this implies is that for the same training performance, we expect smoother networks to have better generalization, according to that upper bound. And the reason I say expect is because for a finite number of data, it's an open problem. What is the best approximation, especially when those data points are arbitrarily placed, as is the case in sort of these deep learning applications where we don't get to pick the training data. So how do you measure, or can you use this as a measure of generalization? Well, you can quantify it using the Sobolev norm, as we talked about, but that's pretty expensive to do for all the nodes in a DNN. Sort of most of this theory on compositional networks sort of requires that the internal nodes are very low dimensional. So you can do it in high dimensions, but it's just very expensive to compute the Sobolev norm. So instead, what we considered in sort of our work or our submission is, what if you consider the complexity of the decision or classification function? And so, for example, in some feature space or even in the input space, if this decision or vector quantizer is very simple, the effective classification function, or the effective operation of the network, or the classification function, would also be simple. So for at a given layer, if this vector quantizer is very complex, it implies that the next layer, the vector quantizer would have to be much more, or the next layer, the neural network would have to be much more complex. So we're hopefully trying to use this as a measure of the overall smoothness or the regularity of the network. And so maybe in communications and information theory, the classic way to do this is using some sort of p-norm through a measure of distortion. And so what we could see is that if you compare input features of the same class and across classes, the separability increases as you go deeper in the network. So this is kind of interesting because it means that the network is projecting these high dimensional images, sort of representations that are more clustered. And this is it's good, but it's also true for well-trained models or models that have good training performance but have poor generalization performance, which is sort of the subject of this competition. So it's easy to predict, for example, if I were given for the same architecture and the same task, it's pretty easy to predict which one is doing better just based on the L2 distance of the features. But if we're, sort of in the format of the competition, we're given, just the, one model, and we have to evaluate sort of its absolute performance, it's a little bit harder to do. So we sort of attributed this maybe to the sort of the not good nature of, sort of less optimal nature of the 2 norm in these high dimensional spaces. So these feature vectors are actually very high dimensional. So we looked at is sort of compressing those feature vectors into lower dimensions. And I think this is something that has been done in the literature, and people have shown this a little bit, but we tried to maybe get a little bit more quantitative feel of what the geometry was. And we did that using Gaussian mixture models to sort of fit multiple mixture components to each of these each of the classes in the training set. So obviously just fitting it, I mean, it'll overfit if you have enough mixture components. So what we did is actually take subsets of the training data and to compute this kernel PCA or dimensionality reduction, and then evaluate basically how different subsets of the training data map to those principal components. And so what that kind of measures is how generalizable or representative a subset of features are, but also gives rise to sort of the distortion matrix that you could use to measure basically how clustered samples are. For example, using the centroid of these mixture components, you can quickly compute the distance. So it does work reasonably well. For example, this is a very good model. This is a very bad model, but along the way, there's a little bit more variability. So another measure that we switch to is using SVMs, and this is a little bit closer to what our thoughts about using a vector quantizer. So as you can see, they're all pretty diagonal, but what we find is that this gives sort of the best measure of distortion. So this idea of distortion is very similar, for example, to the first place winners measurement of clustering. I forgot exactly the index, what it was called, but it's sort of a measure of the intra-cluster variation and the inter-cluster variation as well. So another interesting thing about SVMs is it can directly give a measure of the complexity of at that layer, rather the complexity of the next layer through measure of the number of support vectors. And so if we look at the correlation, this is just the public data set, we can see that this number of support vectors seems to correlate the best. But actually, just looking at the L2 distance between these feature vectors actually does pretty well. But maybe you can come up with a better measure or better metric or better norm. So here's maybe the quantitative numbers of what those correlations were on the public data set. I think on the test data set or the phase 2, the problem is we try to run with number of support vectors, which computing the SVM is quadratic in the number of classes the way we were doing it, quadratic in the number of data points even, right? So we had to really cut that down. And I think that adversely impacted our score. I think that it is a really good measure of complexity. But maybe in the future, what we're hoping to do is use the model weights directly, right? Rather than training a vector quantizer to sort of guess how complicated the next layer should be, we could use the weights of the network itself to measure that. And so, so we're going to leave that maybe for future work. But more generally, maybe this is something we talk about in the roundtable. How do we measure the regularity of a network, and how do we incorporate test data? Because, we're looking at training data for which we have labels, but we may also have unlabeled test data, for example, an STL10 or STL100 or whatever. Maybe there's a way we could use that to measure how regular the network is. And so we have some ideas about this, but I wanted to thank the PGDL organizers. And if you have any questions, feel free to ask them now, or you can send it to these emails here. Thanks for your attention. Maybe there are any questions?
I do have one question. So I'm glad you brought up the, I guess, the feasibility of not the feasibility of the challenge, but whether it is possible to approximate a certain level of performance from only the model and the training data, as I sort of alluded to earlier in the.
Right.
So one thing I was also sort of wondering about before was, is there value in distinguishing between two types of problems? So one of them is the issue of whether we can actually obtain approximations or bounds on performance, and the other one is whether it is a decidable problem or not. So specifically, whether it's computationally feasible to obtain a bound on performance. So is there value in distinguishing the issue of can we obtain a bound on generalizing performance, and whether it is a decidable problem to begin with?
Yeah, I think that's a really good point. So I think the first thing is that this is, maybe the approximation theory approach that I presented is maybe one way to look at it. But I think the problem with these upper bounds in general is that they tend to be weak, right? And so, which is why people try to seek out these empirical measures, because maybe for a certain class of problems, you can get something a little bit stronger, and maybe you don't have to go through all this, first principles theory stuff. But in terms of the upper bound, I think it's pretty clear that, it is possible. With just looking at the training data, but also looking at the model weights, it should be possible. And I think that part itself is very interesting. But Can you remind me again? What is this? You separate it into two classes of problems.
Yeah, like whether it is a decidable problem. So whether we can solve the problem in a
I agree. I don't think that's possible because approximation from point data itself is such an ill-posed problem, right? Like it's really difficult to ask. If I give you a arbitrary finite set of data, what is the best approximation? For every approximation scheme that you come up with, there's very good chance that for some different choice of point data, it's going to fail arbitrarily, or it's not going to be the optimal choice. So how do you measure how generalizable it is if you don't necessarily know where the data lies? There needs to be some consideration of, this is the space of functions, and we don't know the true function here. We're just given point data, the true function being the classification problem. So I think it's not possible, actually, in absolute sense.
Right. I also want to just add a bit points. Like, it is very possible that the function of space that we're searching over is actually much smaller than what we actually think they are, right? Like if you believe the space of function that are looking at is actually smaller, then maybe there's a chance that you just have enough data to actually get a tight bound.
Mm-hmm.
Yeah, basically, I would also like to add a similar thing. So when we try to find like what solutions does a particular algorithm find like gradient descent or stochastic gradient descent, we are basically trying to look at like so not all possible functions representable by a neural net are basically learned by the algorithm, right? So that's the main point, right? We need to bring this to the set of functions which it can actually learn, and then like ask about the complexity of that class. Like just saying that a neural net is over parameterized, that does not mean that it's necessary that on all the data sets it's generalization of performance can't be bounded. So I think that's the viewpoint, like that's my view.
Yeah, I think there's also like a big conflating factor is like what architecture to use. Like, we're assuming that these architectures are the best and they're actually, can capture the full space of like image classification functions based on point data, right? It's all based on someone discovered and came up with this architecture that seems to work. But, maybe it's not the right architecture. Maybe there is a different architecture. We don't know what the structure is. So it's sort of like a chicken and the egg problem almost.
So one comment I have, so basically I find this problem to be very intriguing. So we need to measure margins, but in which space? So like maybe Fourier space is the right choice for images, but I'm not sure. So basically we need to find the right latent space over which these images are defined, and if we measure margin in that space, then basically that should tell us something about the generalization performance. That's my thoughts on this, but yeah.
Yeah, maybe it's like related to representation learning. I'm not really sure, but yeah, I mean, I guess we're hoping that a well-trained network is discovering what those latent spaces are. I think, I don't know, maybe someone else can comment. I don't have lots of experience with that.
Cool. Yeah, we'll have a roundtable at the end. So let's let's move on to the next presenter. So we have On Lee from IBM NTUST. He will play a video, I believe.
it's not audible to me. Is it audible to everyone else?
Yeah, I don't get any audio from
There's
video.
No audio on my side as well.
Let me check with him because he said he cannot speak because probably for late. I think he's muted, but I think you have to. Oh, interesting. Okay, let me. But there's
closely related to need operations and responsible for deep learning. The robustness and the generations of the model are both closely related to whether the model has a good classification boundary. We believe that robustness and the generations have some relevance. So we use robustness decay to evaluate generalization gap by adversarial attack. Here is an introduction to what is an adversarial attack. It is to add some small perturbation to the input sample to cause the model to make classification errors with high confidence levels. In the example, in the figure, add some perturbation to the pandas photo to make the sample cross the visual classification boundary. In addition to the traditional way to perturbing the input, another way is to adjust the weight of the node to make the model perturbed. Both of the methods will be used for our experiments. We define the predictor value of the generalization gap as the model's accuracy in the training set minus the model's accuracy after the adversarial attack. The ranking of the generalization is measured by the robustness of the model. In the part of perturbating the weight of model, we modify the PGD attack from the input to weight. First, set an epsilon as the upper limitation of perturbations, and then set the epsilon of step as the variation of each iteration. Then find the weight combinations that can produce the lowest accuracy in a limited number of iterations, and return the accuracy as the accuracy after the attack, and calculate the generalization. This table records the experimental score of our three algorithms, include the development phase and the final phase. In final phase, the best perform is the perturbating weight. PGD infinitive norm has a big gap in the testing phase. We think it may be because some arguments need to be changed with the model type or size. We will continue to verify the influence of different arguments on the mobility of the algorithm and edit it in the future. In the future, we will try to find out the correlation between robustness and generalization. and prove it with theory. In addition, we will also try to combine the method of evaluating generalization with the model loss function, so that it is not necessary to cut the validation data in the training data and effectively use all the data sets. Thank you for listening to my sharing. This is the end of my report. If you have any question, you can ask on Slack. I will reply it in text. Thank you.
Cool. So that's the last presentation in this section. Now we will have a 24-minute break. We'll reconvene at 50, wherever, like minute 50, wherever you are. Yeah. So see you guys then.
Hi, is Alexiev here?
Yeah, I'm here.
Okay, cool. Yeah, I guess you can start sharing whenever you want.
All right, can you guys see my screen? Sorry, did you say yes?
Yeah. Yes, we can see.
Yeah.
Awesome. All right, well, hello everybody. My name is Valery Alexiev, and I'm an applied machine learning scientist at Cognitive Scale, a startup in Austin, Texas. And today I'll be talking about my submission to this competition called Fractal Dimension Generalization Measure. As an overview, my proposed complexity measure is based on the concept of fractal dimension. The idea being to approximate the fractal dimension of the decision boundaries in the data, as well as the decision boundaries of the provided model. The ratio between the two will signify how close the model is to capturing the structure of the data set and, by extension, its generalization ability. To give a bit of background about fractal dimension, it is a measure of how an object scales differently than the space it's embedded in. Fractal dimension analysis has been previously used in machine learning for dataset analysis, data mining, and feature engineering. I base my generalization measure on the fractal dimension of decision boundaries in particular as a way to measure the complexity of a model. I do this by approximating the fractal dimension through the concept of correlation dimension. Correlation dimension is computed on the class boundary by focusing on examples from different classes. For each batch of data samples, we compute the pairwise distances of samples in the batch, and then count the number of pairs with different classes within distance R for a range of distances. Once we have the counts for each distance, we convert both the counts and the distances to log space, and then fit a line to this data. The slope of this line is the correlation dimension of our data, seen here as D2. Because of the overhead of computing pairwise distances on the entire dataset, we calculate the fractal dimension based on pair counts within a single batch, and then average the results of all batches to get our final estimate of the fractal dimension. Here, you can see an illustration of how pair counting works. The white and black dots here represent samples with different labels. The curve represents the model's decision boundary, while the concentric circles illustrate the range of R's used to count pairs for one particular sample, that black dot in the middle there. So for this example here, pair counting will produce 1, 3, and 5 for each of the R's used respectively. Notice that here we're completely ignoring the model boundary, model decision boundary, and are exploring how the underlying training data behaves. In order to explore beyond the training data, we utilize the mix-up technique, which is a data augmentation technique used to generate new virtual samples by linearly interpolating between pairs of real samples. Here, X1 and X2 are randomly sampled from the training data, and lambda is a mix-in parameter, randomly selected between 0 and 1. Once again, this is an illustration of pair counting after we've applied mix-up. The white and black dots this time represent samples from different model outputs, while the pluses represent the results of the mix-up operation. Similarly, as the previous example, the curve is the model decision boundary, and the concentric circles are the ranges of R. For that black plus in the middle there, our pair counting will produce 0, 1, and 2 respectively, as we're focusing only on the mix-up virtual samples. Combining those two views together, the fractal dimension of the underlying data, as well as the fractal dimension of the decision boundary itself, we get to our generalization measure. My proposed generalization measure, M, is equal to the absolute difference between 1 and the ratio of the correlation dimension of the mix-up augmented class boundary, D2 of X mix-up here, and the training data class boundary, D2 of X, of the model under inspection. The closer M is to 0, the better the model decision boundary matches the complexity of the training data, and therefore the better it generalizes. Here's some results of my experiments. This table presents the conditional mutual information on the 2 public tasks from the competition. As you can see, my technique has 3 hyperparameters. Batch size is the number of samples used to calculate the fractal dimension. The number of batches is how many batches we average over to get to our final estimate of the fractal dimension. And our percentile range is the percentile range of intersample distances that we use to generate our R distances for the pair counting. As you can see, smaller batch sizes tend to underperform. And in particular, when you even reach something like 64 batch size, my algorithm often fail to produce results as the number of samples is too small for the computation of the fractal dimension, because we don't have enough samples of different classes to properly compute the dimension. Similarly, higher upper bound of the R percentile range also tend to underperform. I theorize that this is because at larger scales, the behavior of D2 of X mixup and D2 of X is always very similar, and therefore it is not a good measure of the generalization ability of the model. Intuitively, I would have expected that an increased number of batches would always lead to a better result, since we're averaging over more estimates of the fractal dimension. Experimentally, however, that is not the case. I suspect this indicates that my measure has large variance, but more experiments are needed to confirm this. As conclusion, while my approach is not competitive with the best performing approaches we've seen in this competition, it does provide an alternative direction of research and has ample space for improvement. Some of those improvements include better sampling strategies in order to improve the sampling efficiency of the algorithm, better ways to approximate a decision boundary, so utilizing techniques beyond mix-up, as well as better ways to compute the fractal dimension itself. Thank you for listening, and let me know if you have any questions either here or on the Slack channel.
Hi, it's a very nice talk. I have just one question. Have you tried using just the fractal dimension of the original data without the augmented data?
Yeah, I did try it, and it performed worse than this one. So
okay.
I guess you're talking about
the formula, right? You have a
yeah. So here, instead of calculating the fractal dimension on a mix of data, just using the original model labels. Yeah. So it didn't work really, and I think it's because of the models that we were working with were all trained to very high accuracy. So the fractal dimensions wouldn't be too different between the underlying true labels of the training data and the model outputs.
Oh, okay. So you're looking at the final layer, is it?
Yes. Yeah. This is looking at the final layer.
I'm not sure if you look at the intermediate layer. I'm not sure it helps. Yeah.
Yeah.
Anyway.
Yeah. That's definitely something that's kind of on the to-do list. Is to kind of dive deeper into whether this can be applied on some of the intermediate layers to explore kind of the dynamics of the hidden layers themselves.
I also had one question. So when the number of classes get to around big numbers, like let's say 100, then the batch size 128 is very small for you, right? Because you won't get points from different classes in a batch. So this formula for mix-up won't work well, right?
Yeah, I think that's definitely true. In this setup, I'm definitely doing for each class, I'm doing one versus all, which might help a little bit
Okay.
in that regard when I'm doing the pair counting. So I mean, here is just a binary example, but in general, I'm essentially saying, okay, I'm just counting pairs of different classes within a certain range, rather than pairs of two particular classes when I'm calculating fractal dimension. So that's going to help a little bit, but you are right that with a lot more classes, you need to up the batch size quite a bit.
All right. Any other questions? If not, we can move on to the last presentation of the day.
Thank you again.
Yeah. Thank you very much. It's Simon here. Simon C.
Yeah, I'm here.
Okay, cool. Yeah, feel free to start anytime you want.
Yeah. Okay. Yeah, so hello everyone. First of all, yeah, I'm quite happy to be here. And yeah, I really think this competition and workshop are great opportunities to increase our understanding of generalization. So yeah, thank you to the organizers and participants. So yeah, our submission uses measures of intra-class clustering to predict generalization. And intra-class clustering is a pretty recent idea that is introduced in an iClear submission of this year that I recommend you to read. And I'm going to start this presentation by introducing you to this new idea. So it starts from an interesting observation that in our standard data sets, classes of samples are usually composed of multiple clusters of similarly looking images. So as you can see here on the class 1 of the MNIST dataset and the class R plane of CIFAR10, you can see that the samples of a single class can be grouped into similar clusters, into different clusters sharing visual features. And why is that interesting to us? Well, it is commonly believed that learning structure that is inherent to the data is a key ingredient to generalize well. And so we would expect that models that are able to learn this structure, this clustered structure in the data will generalize better than the models that don't. And so the iClear submission I was talking about makes two hypotheses. The first one is that the ability to identify intra-class clusters implicitly emerges when we train deep neural networks, despite the absence of labels, because these clusters are not associated to labels, and also despite the absence of explicit training mechanism that targets the identification of intra-class clusters. So when we train deep neural networks, we ask them to group samples from the same class together, and we don't implement anything to identify clusters that distinguish samples from the same class. The second hypothesis of the iClear submission is that deep neural networks that are able to identify these intra-class clusters generalize better than those that don't. And to verify this hypothesis, they design 4 different measures that are designed to capture a neural network's ability to identify intra-class clusters. And then they study the correlation between these measures and generalization across variations of 8 hyperparameters. So this is really the same experimental setup as the PGDL competition. And the results are as follows. So they observe kind of strong correlations for all 4 measures across 3 different tasks. And so in the context of the PGDL competition, we decided to use the third measure because it doesn't require label hierarchies which weren't available in the competition. And moreover, it was quite simple to implement and fast to compute. So I'm now going to describe this measure more specifically. So we start from a single neuron and a single class. And the idea is to quantify to what extent this neuron differentiates samples from the class CY. So in this particular example, so these are the pre-activation values of neuron N. And we see that a bimodal shape for class CY, which suggests that this neuron tries to distinguish two groups of samples inside the same class CY, reflecting potentially intra-class clustering ability. And so to measure this, to quantify this, we compute the ratio between the standard deviations associated to the class CY over the standard deviation associated to the complete data set. And if this ratio is high, this would mean that the samples associated to the class are quite dispersed in the neural representation, meaning that the neuron potentially try to differentiate samples from this class. And so this for a single neuron and a single class, and to get the overall picture of neural network's ability to identify intra-class clusters, we simply aggregate first over the neurons through a mean over top k operation. So we take the average over the k neurons which have the highest ratio. And then we aggregate over the classes through a mean operation. Yeah, so this is the measure we used in the competition. So we just tried different values for the k hyperparameter here. And so it's quite simple and also quite fast to compute. It only requires a single forward pass through the network to extract all the pre-activation values. And so we got the 12th position on the leaderboard. And yeah, we believe this supports the intra-class clustering hypothesis. So the result is not that good compared to other results we've seen. But yeah, the intra-class clustering idea is very new, and there's probably more room for improvement. And in particular, we didn't really know how to handle neural networks that are composed of both convolutional layers and fully connected layers. And we believe better measures of intra-class clustering could be designed for such hybrid networks. Yeah, and then, yeah, I also gonna repeat that, yeah, our measure is simple and fast to compute, so we only use 10% of the computational budget. Yeah, so I hope I got your interest about this idea of intra-class clustering. Again, I recommend you to check the ACLEAR submission. And yeah, thank you for listening. I'm looking forward for your questions and the discussion we'll have afterwards. Yeah, thanks.
Cool. Any questions for Simon? Well, if not, we'll be moving on to the roundtable discussion.
Maybe just one question on my side.
Yeah.
So, and did you need any type of data augmentation for this intra-class clustering, or just over the normal data is already good enough?
Yeah, we didn't try data augmentation, so the score is achieved without any form of data augmentation. And so yeah, the pre-activations here that we extracted are used on the training data, the basic training data. We didn't try data augmentation. Potentially, this could also improve the score.
Yeah, for sure. No, I was mostly asking because in the case of intra-class distances, in the case of very bad generalization, you would not have any clusters, and like you would only have one cluster because all elements would merge together. So it's quite nice to see that if the network is able to kind of separate these subclasses, that it works better.
Yeah, probably. Yeah.
Okay, thank you.
Thank you.
All right. Yeah, I guess I'll put my screen share back. So this section is, well, I have prepared some, this is wherever you guys can talk whenever you want. I have prepared a couple of questions or like topics, but if you guys have other things that you want to discuss, feel free to say now. This is just, if there's nothing to talk about, then I have prepared some questions.
Yes, so this first question was something that actually crossed my mind during the competition. So one of the things that we tested at first was just taking a look at the correlations. And it was quite jarring to see that the test error is not that well correlated with the test accuracy. Actually, we had some measures that were more correlated with the test accuracy than the test error.
By test error, you mean the softmax loss?
Yeah, by using the softmax of the, like the negative log likelihoods over the test examples. So that was given to us on the data because we had the training accuracy, the training loss, the test error, and seeing that this measure actually is not that good it's not that correlated with the accuracy. It was quite surprising, at least to me.
So I think one explanation for that has been found in recent work, where they have shown that after some time validation error keeps on going down, but validation loss starts going up. That's because the norm of the predictor starts going up, so the loss scales up, but that norm actually doesn't affect the prediction error, right? Like the 0-1 error. So that could possibly be the reason that why this was happening.
Yes, for sure. Like actually the loss only says anything to you if it's like, if you have 0 loss, you know that you correctly classify, but all the values in the middle, you don't know if you're correctly classifying or not. You just have an idea that smaller values are better, but you don't know, it's not directly correlated with the accuracy, but it was quite surprising to see that even some measures with only the training set were better than this.
Yeah.
Anyone else?
So one thing that I still need to find, like, I don't know, but so I expected noise-based measures to work well, because that has been the underlying principle for many generalization bounds recently. But I think, as Professor Sanjeev Arora also pointed out, that it has been shown in this new NeurIPS that holds for random labels as well. So probably I was wrong. So yeah.
I see. Yeah, actually, that I was very surprised by that paper too. Well, I mean, we can always come back to these questions if you guys think of anything. Yes.
Regarding the noise based, so we had a chance to try out an adversarial based kind of test on these models, and so I think everyone agrees that like the adversarial test accuracy on these models is probably like one of the better generalization measures, right? So if but what we kind of observed was that it does not correlate at all with these particular models that are there in the public data set. Yes. So one thing is that like the kind of adversarial tests that we ran were the Carlini, Wagner, and other iterative kind of adversarial tests. So probably these simple models like the network architecture and others, or simple like 3 or 4 layered networks would probably, I would assume that they would not definitely hold up to these kind of hard tests. But like probably maybe in kind of like future competitions, maybe that, I think because what we observed was that once if you test these models with these adversarially perturbed samples, it does not correlate at all with the test accuracy. So even the best performing the models, like which has very good test accuracy, like fall down really rapidly, and then there's no way for you to actually measure which model is a better one, which model is a bad one. So maybe, yeah, I think maybe if you try with a more which like models which are known to be resilient towards this, maybe we can get a better sense of generalization in terms of like empirical value of what we are trying to find out.
Yeah, my feeling about adversarial perturbations is that they just don't really represent the image that you actually see, right? It seems.
So my take is that like most of the nets who are not actually trained in a robust way generally have a bad adversarial accuracy. So I don't think we can actually quantify generalization using adversarial accuracy, because it has been shown in papers as well that even networks which have a good test error, they generally have a bad adversarial accuracy. So
yeah,
I will not call them as out of distribution, but
right. I agree that the adversarial test accuracies are generally not how we, at least in this competition, how we are defining the generalization to be. But I think in a more conceptual kind of sense, I think the adversarial accuracy adds a dimension to this generalization. If not exactly define the generalization, but what I mean to say is, like, if you're given a model which has really good adversarial test accuracy, you may be inclined to say that model is a good.
Yes, definitely. I agree with this, that a model that is robust will be generalizable, but a generalizable model will be robust. That's something I don't think.
Yeah, it hasn't been proven, but it's kind of an open problem. But yeah, if given what I wanted to say was, like, if you are given models in the data set which in the competition, you might be inclined to add this dimension as well and test on the adversarial accuracy and maybe approach this problem from that side. Maybe we can prove that in some sense.
Got it.
All right. So we can move on to the second question. Yeah, I think I prepared 4. Maybe we'll have time to go through all of them. Yeah. So the second question is, obviously the format of competitions is really new, and then I acknowledge that there are a lot of places that we could have improved. So we're just generally wondering, do you think this is a good way to learn about generalization deep learning? Or like, maybe it seems like you guys have been studying the problem for quite a while already. Or like, do you learn new things? Or what do you think are the disadvantages of the format, like the drawbacks, limitations, things like that?
Oh, one thing that the complexity measure does not, I think, accommodate is that we do not know what the test set will be. So if the test set has a different distribution than the training set, then we will have no way of knowing how different that is. So if the test set was given without the labels, maybe we would have a more generalized complexity measure. So
but
I was just thinking that if the train set distribution and the test set distribution were very different, then the accuracy would naturally be lower, and we'll have a more larger generalization gap. So it depends on the data set, right? So
But
we
but the test data is drawn ID from, well, okay, in some sense ID from the same distribution, right? So they should follow the same. Or am I?
I mean, for the competition, it's okay. But if we look at some real data sets, some of them have a somewhat different distribution. And for...
Oh, right. Yeah. Yes. Yes. Okay. I see. So we're talking about like distribution shift. Or...
Yeah, distribution shift. So the complexity measure, if we were to define a complexity measure, we should be able to define it for how well the generalization would be for a different distribution shift as well.
I see. Yeah, that so we actually had that planned at some point, but in the end we decided, since this was the first time we're running this, it's already quite ambitious. So in the end we decided to stick to the most basic IID setting. But yes, I agree. The distribution shift is technically a more useful notion of generalization. Yes.
Another thing to consider maybe in the future would be to include other types of tasks outside of vision classification models.
Yes, definitely. I totally agree.
I think this was well chosen in terms of what tasks we have to predict generalization for.
Yeah, in personally, I definitely think there's a downside if we only look at visions. I think images, they have a very particular type of structures that maybe we're overfitting our theory to. But again, maybe that assumption is necessary if you want to get something that actually works well in practice. Yeah.
So I think that it's we are not very sure that whether we can have a generalization metric for both a transformer and a CNN, just the same generalization metric. So kind of language models and computer vision task kind of thing. So that's, quite hard to get.
Yeah, it's really hard to imagine that such thing exists, right? But maybe. Well, I don't think it's too far-fetched, right? Because there is a very popular model of these data is the sparse coding model, right? You can actually, both images and language can be modeled by the same sparse coding model, or like some variation of sparse coding model. So maybe it's not too far-fetched to believe that you could have something that works for images and languages. Yeah, but I'm not sure what that would look like. Yeah, it's a definitely interesting question to think about. Also, I guess language, there's just so much data that it's not really a problem.
Yeah, and like the notion of generalizability is also quite different in language. I'm guessing compared to images.
Yeah, I think maybe to speak to that is I think coming up with what is the definition of generalization exactly, right? When you're saying like test set performance, like part of it is like, okay, well, if you use a different test set, you're going to get a different generalization gap. That's definitely true. Is it the maximum amount of error? Is the average error in sort of over the whole domain, or how do we define that? And then another sort of in the format of this competition, though, it was like, evaluate each network independently or each model independently. Whereas, there is there, I don't know, maybe this is like a question for the roundtable, right? Is there like value in doing like comparative performance? So given two models at a time, you can predict which one's better by X amount or something.
Oh, interesting. Well, the metric underlying it is actually doing a pairwise comparison, right? So I guess what you're suggesting is you should.
I think this is a ranking task, right? So we are indeed doing just that. Like, indeed we are just doing ranking, right? So there is no difference if the ranks do not change. That doesn't matter to, like, basically that's what the task is.
I mean, it requires that the ordering you make is true in like absolute sense, right? Like whatever complexity measure you're predicting, it needs to rank well regardless of which models you're comparing, right? But if you just had two models, for example, you could have a pretty bad score, but if you're given two models, you could say which one is better if you only just compared those two models. But the absolute scores for each of them, may be meaningless.
Right, but that's
I don't know how to say that.
That's exactly what the metric is capturing, right? Like the metric does not care about absolute value; it cares about comparison.
Right, but the way in which you make that number doesn't depend on the value of other models, right? It only depends on the single model that you're looking at. Is what I'm saying.
Yeah. Okay. Yeah. Yes, I see what you mean. Yeah. So that sounds very expensive, though. If you want to.
Yeah, definitely expensive. No, I mean, I just wanted to bring it up as maybe ask, like,
Yeah.
I think there's value in that. I don't know. Like, obviously, it'd be great if we just predict the absolute generalization gap very directly, but I don't know. Do other people see value? If not, maybe it's
just so I
something
understand
else to
correctly.
think about.
Yeah. So just so I understand correctly, you're basically saying, like, suppose there are two models, one with 95% accuracy, one with 90. So the first model has half the error rate as the second one, right? To 95 to 90. So you're saying, can we compare like relative performances? Like 95 to 90 would be equivalent in error rate as a comparison of 90 to 80, because again, the error rate is a half for the 90 model compared to the 80 model. Something like that.
Yeah, it could be like that, just trying to predict the number as well, but it can also be, much simpler, like the 90% model is worse than, binary decision. The 90% model is worse than the 95% model. And then if you compared the 90% model and the 80% model, then the 80%.
So it's a relative comparison, like some relative comparison.
Right. Relative comparison, exactly. But whereas the complexity measure is basically for the 90% model or the 80% model, this doesn't need to line up exactly as in a row, like 80, 90, 95, if that makes sense.
Right.
However, would this give us an intuition about why does deep learning generalize then? Because then, like, if we are creating a measure which is like which is a function of two models which we take in, then the whole then if it's not separable in these two arguments, then it's quite difficult to pinpoint the thing which is which makes the deep network generalize. Like that's the main point of this. That's the goal that we want to reach, right? Or do you think?
Well, I certainly there is if you just care about practice, then that's certainly useful, right? You just want to compare two models. I mean, I don't think that's too unreasonable to assume. Why?
Okay.
Well, at least that's my opinion. I mean, this is a roundtable. So I guess there are some people who try to use parametric models. So it's not dependent on two models, but it's dependent on the entire population model, right? Now that becomes like a regression problem essentially. Is that like an extreme form of what you were thinking about? Like just train another meta function on top of every single function, and then try to.
Yeah, I sort of view that as not maybe like the right application of it. It seems infeasible to actually do that well for large number of models and tasks and stuff. And I sort of wasn't thinking that, but.
I mean, actually, you'll be surprised. So if you can find the right feature, it seems like they actually do reasonably well. So, I mean, I have written a paper on that, and then there are some other competitors who also did that at the beginning of the competition, and they got a pretty good score. But I think they ultimately decided to do something else. But yeah, is it like it is possible, like find some patterns in this statistics that signify generalization? Yeah. Anyway,
But if those numbers change with changing data set, then we don't learn anything useful from it. Like we learn that okay, given a data set, we can train a measure that works well, but it should work like the basically the weight should remain the same when we change the data set as well. Otherwise,
well, I
we are
mean,
just
I can train on more than one data set, right? I mean, it's a pretty intractable problem. I do agree, but it's the fact is that someone tried it and it did seem to work, right? Going from the public data, I assume they trained it on the public data, right? And then they applied to phase one, which was completely different from public data, which was somewhat an intentional decision. Yeah, and then it magically somehow works, which yeah. So maybe there is some.
Yeah, I guess my opinion is that I wouldn't tend towards doing something like that personally, right? And I accept that there are methods and they seem to work well, and that makes sense. But I do think, like, on the contrary to my own opinion, right? Like, we talked a little bit about like narrowing the function class, or like understanding maybe the space of functions, of like image classification functions, for example, and sort of narrowing the scope like that, by looking at all these hyperparameters. It seems like it does exactly that, right? We're trying to like narrow the scope of what are the space of possible functions and networks, and can we like study specifically the generalization of those, as opposed to having just like a very general, first principles function approximation, viewpoint.
I see.
So
yeah.
I think that, I mean, I accept that there's value. I just, like, for myself, I don't know how to pose it in a tractable way. So, but maybe, I'll take a look at your papers.
Well, I mean, the paper was done at Google, so it's probably out of reach for most of.
It's tractable for Google.
Yes, it's tractable for Google. Yeah, I think that's a good way to put it. Yeah. But yeah, I mean, I guess it was an interesting question to ask, I guess, in some sense. Yeah. Cool. Yeah.
The evaluation measure that's being used to evaluate the complexity measure. So in your evaluation to compute the entropy, you're basically giving the same weightage to each of the hyperparameters. Like, for example, in the VGC style, you have 8 or 9 or something kind of hyperparameters, and you're basically giving the same kind of weightage to, let's say, batch size, and same kind of weightage to the dropout.
It's not quite, actually. It's normalized by the entropy itself, right? So the entropy is somewhat captured. Sorry, is that the question you were asking? Sorry, finished. Sorry. Yeah.
I think maybe I kind of misunderstood. I mean, I kind of misunderstood reading from the code probably, but yeah. What I wanted to say was, what I understood was you were kind of giving same weightage to all kinds of hyperparameters equally, and I thought maybe that would in some way it might be doing disservice to, especially because we don't know which hyperparameter is kind of more correlated with the network generalization. So I just wanted to say, okay, maybe have you tried giving different kinds of weights to each hyperparameter and then computing entropy?
I see.
Yeah.
Okay, so I think I understood what you're asking. And that I think the concern is actually already kind of addressed in the code, or in the metric. So think about it this way, right? So you have a bunch of hyperparameters. If a hyperparameter is useful, then you would expect the problem to be to have a relatively low entropy condition on that hyperparameter, right? Like
Yeah.
Like the behavioral model is very predictable.
Right.
Conditional that model, hyperparameter. And then if a model is a hyperparameter is not as useful, then you would observe a relatively high entropy distribution, because it's random basically. Like it doesn't give any new. It doesn't give too much information about how the model will generalize. And then that entropy is actually the upper bound of the mutual information quantity in the numerator. And then we normalize the numerator by the entropy, so all of them can be at maximum be 1, right? And then if it's uninformative, then so in that sense, it already kind of it's a weighted comparison, right? Or does it not?
Yeah, I guess my question is, so for example, let's take two models which only differ in the network architecture and hyperparameters by just, let's say, dropout. So
okay,
we have two models which are essentially same, trained on the same data, everything same, except their dropouts are different. Now, so I have a complexity measure which gives me some value on this first model and a different value on the second model.
Okay.
Now, what I meant to say was like, so for when you're comparing between these two models, you're basically weighting them with the relative error in the test accuracy correctly, but does that actually correlate with the difference that the complexity measure is producing? I don't know if it makes sense. Yeah, I'm not able to formulate this exactly, but
yeah, I guess I'm not sure what. I mean, we can always discuss this. Like
yeah, in Slack, yeah, yeah. It's been a long time since I went through the code. Maybe I need to.
Yeah. No, you just feel free to either message me on Slack or email me. Yeah, I will try to respond.
Yeah, sure. Yeah. Thank you.
Yeah. Any other points on this? We have a few more topics. All right. Once, twice. All right, next one. Yeah, so what are your thoughts on data augmentation? I'm sure this has crossed many of your minds. So I kind of want to get a sense of what people think about data augmentation as a way of measuring generalization.
I have a conceptual question, and maybe this is the right form, maybe not, but I have a conceptual problem with this idea of mix-up. It doesn't make sense to me. If you average two images of a dog, it doesn't look like a dog image, and it shouldn't be classified as one. So I don't understand. I mean, it's great that it correlates well with generalization performance, but I don't know, maybe someone else can explain it, but to me, it doesn't really make sense. And if that makes sense.
Yeah, I mean, I don't think mix-up in the input space can make sense.
If it doesn't make sense in the input space, how do we understand it in the feature space too, right?
Yes, so I was one of the ones that used mix-up, and to me, it's mostly the idea of like trying to analyze the space and how the function interprets the space more than how the real image is used. In the case where you want your image to make some sense, you should probably be using something like cutout mix-up or things like that, where you, instead of just mixing the pixels, you're doing cuts of the image. And so you have like a dog with a head of a cat or something like that. And in this case, it's nice to see if the model at least thinks that it's dogs and cats and doesn't go like to airplanes and things like that. But mostly, I would prefer not doing data augmentation in this case, but it's quite hard to separate the complete overfitting case if you're not using data augmentation, at least in the measures that we tested.
Yeah, I just want to say. Oh, sorry. Go ahead.
Sorry. Go ahead.
Oh, I was gonna say, yeah. You guys saw it earlier in the phase 2 we added data optimization to our models, which was also an attempt to I guess make it not as effective. It seems like you can still find something that worked quite well, which I find very surprising. But anyway,
So yeah, I definitely thought that when we use data augmentation, using that we should definitely be able to predict test error. But I am surprised that it didn't happen. Like basically, this is like a different test set that we have, and definitely like probably this is not exactly IID, but it is close to a test set that we have. So we can just like feed into the model and just check the test accuracy. But I'm surprised that this didn't work well. So yeah.
Well, it did work very well on the phase 1, right? Like
yeah, it worked very well on phase 1, but I'm surprised it didn't work well on phase 2. Maybe because of the third data set where data augmentation is pretty hard. So on fashion MNIST, I'll say like rotating the things, etc., is probably less sensible as compared to others, or maybe.
Well, I guess the point here is that data augmentation makes a very strong assumption about your input data, right? Like, which is in some sense somewhat restricting. That's my opinion.
Yes, for sure. And there's another problem is that you kind of have to hope that the models were not trained with the data augmentation that you choose. So for example, I'm almost sure that if the models that we were being evaluated on, they were trained using Mixup, you would not have like the first and the third place using Mixup, and I think maybe the second one too. So it kind of becomes like a game of cat and mouse where you have to try to find the data augmentation that's not used by the model, because if you use the one that the model was trained on, it's not going to help you very much.
Well, I mean, ultimately, we actually the thing that we care more about is improving our performance rather than predicting generalization, right? The competition hopes to find something that will work. We already know that data augmentation works. So in that sense, I guess it's not too surprising that it works extremely well, because if you train directly improve generalization, then obviously it's capturing something about generalization, right? But that doesn't, at least personally, I don't feel that's too insightful. Or using mix-up is actually
maybe coming up with a general augmentation technique is. So I agree that if we can find that mix-up works well, then that is not like specific to like a particular data set that we can.
So I think mix-up is perfectly fine. It's I find like if you're putting other parts on it, like I guess mix-up is also assuming the topology of your input data, but that's a super general assumption. But things like rotation or like saturation adjustment, these things, it kind of relies on a very specific assumption about the data, which makes it kind of hard to. It's kind of, I guess, not elegant for my taste.
No, I completely agree with you. We only started using data augmentation because actually in the public set, the best models that we had were not using data augmentation. But as soon as we got to the development one, was impossible without data augmentation.
Yeah, I'm just commenting on the fact that when I data change it, like for example, I think using mix-up is fine, because mix-up does not assume anything about data other than the fact you can do some adding, right? Yeah, cool. Any other thoughts? Okay, going once, going twice. 4. Okay, let's move to the next one then. Oh yeah, the next one is what do you think about it? I guess we already kind of discussed this. So like training another parametric model on top of your models and hoping that it will work.
Yeah, it would be kind of nice if we could actually use these complexity measures during training, right?
I think it has some value in the sense that if we can find the correct set of features which help us to predict generalization, then maybe we can like try to get some abstraction out of it. Like why are these features the one which are predictive of generalization? So
Any other opinion? Yeah, I guess it's been going on for a while. The last question we have is well, what's your suggestions or how, like, for next iteration, if it happens, what do you guys want to see? Like what models, what changes in the protocol, or just in general, anything you guys think if you were to change the competition, how would you change it?
I think maybe having an idea of how different the test or the private test set is. Like, for example, number of classes. I think there are probably several people for several teams for which, including my team, for which it didn't scale because we just didn't even know.
Yeah, that was definitely not, well, like we did not anticipate that. Which is, I guess, that's a very good point. Yeah, we should definitely. But then, like, is there any other way you think you can scale it down? Like you said, you have something that works really well on phase 1 and also public data, but that method will not scale to large number of classes, or do you think there's like computational, like if you spend more time, you can be more efficient?
Yeah, I think there's either tricks we could do. Like, I speak for my team, but there's probably tricks we could do. But there's also different methods we would try, right? If we knew that there was
that was an oversight.
No, it's all good. We really appreciate putting this competition together. I appreciate that it takes a lot of time and effort to do that. So I think it was really, really good first pass, but obviously there's small nitpicks that we can improve.
Yes, for sure. I would also like to thank you guys for hosting the competition and creating this data set that will probably help people continue working on this.
Yeah, that's the hope. We will. Next week is the time.
No. I didn't want to.
Thanks a lot.
I didn't want to put more pressure. I was just saying like thank you because I just can't imagine the amount of problems that you guys had, like trying to balance all the submissions and everything. And
I mean, these things are. It turns out it's easier if you have a lot of GPUs.
Yeah, that's.
I'd also like to say thanks, and I think it was a really important competition because a lot of the big sort of improvements we see in machine learning have been because of the ability to benchmark performances across different groups. So, like the ability to benchmark something like generalization performance is really useful. So, yeah, again, thanks.
Yeah, no, definitely. Thank you guys for participating. I mean, if you didn't come, then there will be no point. I mean, on that, so this field has largely been very theory-driven, I would say. And then I think we are starting to realize the limitations of we only look for things from the first principle, and then this was meant as a, I guess, a potential remedy to that problem. And then I think it definitely served its purpose. And then so we're also just waiting for feedbacks from you guys, from the general community, and then to see if they think there's a value to, or like if we should hold next one, and then what kind of task we should do, things like that. Yeah.
Like doing language tasks is sort of hard because like we already have the data for it on the web. So I don't know, like getting the generalization performance for language tasks seems kind of hard.
Yeah, no, I mean, I definitely agree. Also,
what do you think about? What do you think about the version that involves tabular data sets?
I guess it's probably not clear to them what tabular data sets mean, right? It seems like.
Oh yeah.
I guess you can give a description.
Yeah. So tabular data set is more like you have like the input is a vector of either floats or integers, and the output is just then the output is a category. So that's just a normal tabular data set where you don't know the number of columns, and you don't know the distribution. You don't know what each column means, and you want to see if it's possible to predict the generalization gap for a neural network trained on this kind of data set.
I think that's a good data set, because then we won't have like the augmentation as well. So like people can't do some other trick to get like the final generalization performance, right? So I think that's a nice baseline to have, definitely, but I don't know how much practically useful it will be, because like in my knowledge, I don't know like many tabular data sets on which neural nets are being used practically. Like most of their applications are in CV or in NLP, but definitely this makes sense as a way to get a generalization bound.
Well, in the limit, every neural network problem is a tabular data set, right?
Yeah.
But I agree with your point that in practice, for those sort of what we consider like, maybe simple or table data, maybe like people use logistic regression or something like that. But yeah, I do think there's still value in it.
Yeah, tabular data is, I think neural networks are definitely used on tabular data sets, especially where there are, where you have an embedding for the trained on the categorical features. So yeah, we do see some cases where we use neural networks on tabular data, and they do perform better than random forest or logistic regression. So it is actually useful if we can come up with some way to predict the generalization gap for a tabular data set, and hopefully use that to drive better algorithms for training those DNNs. Yeah.
Cool. Any other suggestions? Opinion? Well, if there is not anything else, I think we are at the end of the live events. I think
I would just like to say thanks for organizing this competition. Like
no worries.
So,
it was very fun actually. I mean, obviously sometimes it got there's a lot of work, but actually I myself learned a lot of new things. Like I was watching presentations, a lot of things you guys talk about I was not aware of, and I consider myself to be reasonably knowledgeable of the field. So quite eye opening. Yeah.
Yeah,
cool.
thank you for feeding.
Yeah. Cool. Yeah. So thank you guys for participating in the competition and also coming to this workshop. I hope everyone had fun in this competition, despite all the server failures that we experienced. Yeah. Thank you. Yeah. If you guys have any more questions or yeah, just feel free to message us on Slack or email us. Yeah. Cool. All right. See you guys.
Okay, thank you.
Okay,
See ya.
thanks.
Yeah.
Thank you.
Yeah, thank you.
Okay.